Well, good morning or afternoon, ladies and gentlemen. It's your daily dose of Dorfler. It's been a few days since you've had your daily dose of Dorfler, but we are back at it again for the final chapter of the semester. I can't believe we are already at this point, but we are, and we're going to rock and roll in chapter 4. Now, if you have not already checked your scores on on your super quiz from the last half of chapter 3, go ahead and take a peek at those. Overall, I was really happy with them, so good job on those. So obviously, we're going to be making a lot of not a lot of changes, but obviously everything's going to be virtual from here on out, at least until the end of this semester. So I'll be making some changes to some quizzes that I had kind of made up. I'll be modifying and adding and subtracting some of the questions. So it's going to be a little different. And when we get closer to the time of your first quiz, then we will kind of talk a little more about that. And right now I have penciled in that your first quiz will be over the first 3 sections of chapter 4. And I believe it's going to be on December 7th, which is a Monday. So one other thing is, and I'll put this in the message with this video when I post it, is stay looking at plan book, because plan book is what I will be using to kind of show you what the daily and weekly plans are again. They should all be ready to go all the way through the end of the semester. So you take a peek at those on a daily basis. And I think that is about it. All right, let me kind of get this. I'm already having issues with... Okay, let's get back into it. Anyway, what chapter 4 is discussing is reactions in aqueous solutions. Really, it's just anything that's involving like wet chemistry. So usually you're going to have a type of solvent involved, which is typically water, but we typically don't really investigate water's role in a lot of these reactions. They just kind of provide us a medium, if you will, in our reaction. So in those first sections, we're going to have some terminology that we've got to know, okay? With this video, I'll also be posting your new chapter materials. I'll be posting a second post today for your homework assignment. It's going to be a real quick homework assignment. That's going to just go over everything we've covered in section 1, okay? It'll be due tomorrow, so make sure you pay attention to that. Excuse me. Anyway, got to get the old rust off my gears here as well. So let's start. Since we're talking about aqueous solutions, we got to know what a solution is, okay? It's defined as a homogeneous mixture of 2 or more pure substances. Now, the idea of pure substances goes way back to chapter 1, I believe, when we classified matter. Now, in a solution, we have 2 parts. We've got the solvent and we have the solute, okay? The solvent is, as I mentioned, is typically like water, some type of liquid, but in reality, it's the substance that is in the greatest abundance, whatever you have the most of. So sometimes it's not always going to be water. Then we have solute. It's all the other substances. Okay, so imagine if we had a scenario to where we had a big glass of water and an ounce of chocolate powder. Like you're going to make hot chocolate or chocolate syrup if you do chocolate milk, or I don't care what you do, but you get what I'm saying. The solute would be the chocolate because it's in the lowest amount of substance. The solvent would be the water because it's going to have the greatest amount of substance. All right. Now, this word right here, this pretty word right here, dissociation. Okay. Let's think about what that word means. Okay. When we associate with people, that typically means that we hang out, we come together. When we dissociate, it's going to be the exact opposite. So we're going to separate, spread apart. And this is what's happening when we have certain substances placed in a solvent, okay? When we have ionic substances, okay, ionic substances can dissolve in water. Most of them can dissolve in water. I shouldn't say all, but most can. What's going to happen is the solvent is going to pull the individual ions from the crystal and solvate them. I love that word, solvate. Now, what solvate means is this, okay? So here we have a crystal of sodium chloride. Okay, sodium is positively charged ions and chloride is negatively charged ion when they are by themselves. Water molecules will come over to this crystal structure for sodium chloride, and it begins to essentially rip it apart savagely, okay? Water is what we call a polar molecule, okay? We've got a slightly positive side where the hydrogens, which are these little white Mickey Mouse ears, are, okay? And then the oxygen, which is the big red one, it has more of a slightly negative charge. It does that because of something we'll learn later on in the year where they don't have equal sharing of electrons, okay? Oxygen likes to pull electrons much stronger than the hydrogens, so we kind of have an imbalance in sharing of electron charges. So anyway, when it solvates this, so you see here, we've got the green chloride ion and the purple sodium ion. The act of solvating is we see that the water molecules around the chlorine ion, the water molecules will kind of orient themselves to where they will have their more positively charged hydrogen ends surround that ion. And just the opposite for the sodium. The more negatively charged end of the oxygen will congregate and orient themselves towards the positively charged sodium, and it completely engulfs those ions. So that's why if you make salt water, when you pour the salt crystals into the water and you stir it up and you dissolve them, that's why it seems to disappear, because those crystals are being ripped apart by the water molecules and basically are being hidden or masked by the individual water molecules themselves. So that's what's occurring when we have this. But the real term is called dissociation. I'm going to be using that term a lot, okay? Dissociation. I don't care if you have to write it down 10 times, highlight it, arrow it, whatever you need to do. Make sure you get that term under your belt. So certain substances will dissociate, and those substances are called electrolytes, and we have varying degrees of electrolytes. What an electrolyte is a substance that dissociates in ions when dissolved in water, okay? Think about when you hear that term electrolyte. What might bring to mind when you hear that term? Some of you may say Gatorade, and you'd be 100% correct. Gatorade helps replenish any of the essentially the ions that have been lost from the body when the body sweats. If you've ever been sweating and you let the sweat dry and you notice on some of your clothing or maybe even your skin, you've got like these white flakes or this white substance on you. That's the salts that have been removed from your body, and you need to replenish those because your body relies heavily on ions, because ions can help transmit certain electrical messages from your body, and we need to have those in order to function properly. So that's what's happening in Gatorade. We have certain substances called electrolytes. They could be various types of salts that are placed in these typically water solutions, and we drink them to help maintain our body's performance. We have electrolytes and non-electrolytes, where you could probably guess what the difference between those is. Electrolytes are those that dissociate into their ionic components. A non-electrolyte is something that may dissolve in water, but does not dissociate into its ionic substances. So we got those two broad categories of electrolyte and non-electrolyte. Okay. Now, this is a really good table to know, table 4.3. Soluble ionic compounds tend to be electrolytes. Now, they say tend to be, or you could even replace it with typically. Okay. There are some ionic compounds that are not soluble, and that's going to be one of the main points of emphasis throughout this chapter, is identifying substances that, are not soluble. Okay. So anyway, what makes a strong electrolyte? Okay. Well, ionic compounds. Typically all ionic compounds, are going to be strong electrolytes. So will strong acids. Okay, we're going to talk about a table of strong acids. There are 7 strong acids that we need to know while we're doing this type of work. I also want you to add underneath strong electrolyte for molecular type compounds are strong bases. Okay, there are about 8 strong bases, 7 strong acids. Okay, we're going to talk about those here in a minute. Weak electrolytes are electrolytes that, yeah, they'll have some dissociation, but a lot of times as molecules are dissociating, so splitting apart, others are reforming. So you don't get a complete dissociation occurring with weak electrolytes. There are no weak electrolytes that are ionic compounds. We do, however, have weak acids and weak bases, which make weak electrolytes. And lastly, non-electrolytes. Again, there are no non-electrolytic ionic compounds. We've got all sorts of other compounds that are molecular in nature but non-electrolytic. So think about that chocolate powder that I talked about just a few moments ago. Yeah, it can dissolve, but it's not going to dissociate. Therefore, it's not an electrolyte. So again, molecular compounds tend to be non-electrolytes except for acids and bases. Now, a really cool experiment that we could do if we could have people here is this light experiment here. If we were to hook up a light bulb to pure water, you'll see that the light bulb does not shine. If we add sucrose, which is a non-electrolyte, it's a molecular compound, dissolve it, does not dissociate, the light itself, again, does not light. But if we add salt, sodium chloride, which is an ionic compound, therefore it's an electrolyte, we see that as that water is solvating the sodium chloride crystals, the sodium chloride crystals are dissociating into their charged ions. And those charged ions are going to allow for the conduction of electricity. And we see that the light bulb will light. So it's a really neat experiment. Just too bad we can't do it right now. It wouldn't be a really good version of it through the camera, just because this isn't the highest quality camera. It's really something you need to see in person. All right, this is the table that you really need to have bookmarked, highlight. Again, whatever is going to make it call to your attention. Okay. We have common strong acids and bases. Strong acids, strong bases are considered strong electrolytes, so they will dissociate when mixed in water. So we have hydrochloric acid, hydrobromic, hydroiodic, chloric, perchloric, nitric, and sulfuric. Okay? You need to know those 7. For strong bases, you have group 1 metal hydroxides and heavy group 2A metal hydroxides. Now, when we say metal hydroxides, again, group 1A and 2A, they are metals on the periodic table. Now, what typically makes a base is the fact that it's got this hydroxide, this OH polyatomic ion right here. So, examples of strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. And for the heavier group 2, meaning those that are lower down on the table, calcium hydroxide, strontium hydroxide, and barium hydroxide. Okay, so these you will need to know. Okay, so to run it down, what makes a strong electrolyte? Strong acids, strong bases, and soluble ionic salts. Okay, so we're going to just talk through this practice, sample exercise, and do our practice, and then we're going to be done for today. So let's look at this real quick. The accompanying diagram represents an aqueous solution of either magnesium chloride, potassium chloride, or potassium sulfate. Which solution does the drawing best represent? Well, there's a couple different ways that we can approach this question. One of the first things we could probably do is look at the ratio. Okay, we've got negative ions, or negative spheres that represent ions, and we have spheres that represent positive ions. Let's look at the ratio. Okay, in terms of positive, we've got 1, 2, 3, 4, 5, 6, 7, 8 positive ions. For negative, we have 1, 2, 3, 4. Okay, so really we have a 2-to-1 positive to negative ion ratio. But we could also kind of be sneaky and take a look at the charges themselves. Okay, the positive charges are just a +1. The negative charges are -2. So we could go up here and look at, okay, which of the anions are going to have a charge of -2. Does chlorine? Well, chlorine's in group 7. Group 7 elements typically make a -1. Okay, so these two kind of are not looking so good. Sulfate, SO4, calling back to chapter 2, it does have a 2- charge. So if we think about it, if we have potassium sulfate, it has a 2-to-1 ratio. It has 2 potassiums for every 1 sulfate. So the ratio is a 2-to-1. If we were to compare it to the other ones, magnesium chloride, magnesium is a 1 positive to 2 negative. Okay? We don't have that here. And potassium chloride is a 1-to-1. So the only thing that works based off of looking at ratios of positive to negative ions, as well as the charges that match up with their correct ions, would be that this diagram here represents potassium sulfate. Start looking at the other one here. So we're going to take that concept and look at something else here. So imagine if you had 4 diagrams, okay? If you were to draw diagrams representing aqueous solutions of nickel sulfate, calcium nitrate, sodium phosphate, and aluminum sulfate, how many anions would you show if each diagram contains 6 cations? Okay, so what I'm going to do, if I can do this cleanly, it's a lot easier to do this on a bigger board, is I am just going to go ahead and draw out my 6, there we go, draw out 6 cations, okay? 6 cations. There are going to be 6 cations for every scenario here. So, nickel sulfate, okay? We have to look at the ratios here, okay? Nickel and sulfate is a 1-to-1, okay? So we need to figure out how many anions would be present if we had 6 cations. Again, it's a 1-to-1 ratio because I'm looking at subscripts here. Now, we don't look at this 4 as a subscript because that is part of the polyatomic ion of sulfate itself. So for this one, we would have 6, 1, 2, 3, 4, 5, 6, 6 anions. And that's just the answer for that one. Okay? So there's our second one. Okay? Calcium nitrate. Calcium nitrate has a formula of Ca parentheses NO3 close parentheses 2. So it has a ratio of 1 cation for every 2 nitrates. So if we have 6 cations and it takes 2 nitrates for every 1 cation, we're going to have, count with me here, we're going to have 12. Again, it's all about the ratio here. Again, calcium nitrate is a 1-to-2 ratio. For every 1 cation, we have to have 2 anions. So we've got 2, 4, 6, 8, 10, 12 anions for calcium nitrate. Let's get that written down. We've got 2 more, so I need some room, so I'm going to erase these. Our next one is going to be sodium phosphate, Na3PO4. Now let's go ahead and write the last one of aluminum sulfate Al2SO4 3. Okay, so again, looking at the ratios. For every 3 cations in sodium phosphate, there's only going to be 1 anion. Okay, so it's a 3-to-1 ratio. Okay, sodium has that subscript of 3 here. So if I have 6 cations and it's 3 cations for every 1 anion, I'm only going to have 2 anions for sodium phosphate. And last but not least, aluminum sulfate, 2 cations for every 3 anions. Okay, so I've got 6 here. So I'm just going to draw that again. Okay, so I've got 6 total cations, and it's a 2-to-3 ratio. For every 2, I need 3 anions. So for every 2, again, 3 anions. So that means 3, 6, 9. I mean 9 anions. It's just simply like multiplication, division, whatever you need to do that. Okay, so again, it's all about the ratios of cations to anions. All right, now that's going to put a wrap to this first section. I'll be posting this video in conjunction with your notes, your PowerPoint notes, your Google Slides, your problem set questions, and your Chapter 4 test review. Now, as I mentioned, the quiz over the first 3 sections will be, actually, I'm sorry, it's only going to be over sections 2 and 3, okay? But all 3 of your first sections of problem set questions need to be turned in on Monday, December 7th, okay? And I'll be posting that throughout the week, so just pay careful attention. With that being said, keep an eye out for all the posts that are going to be coming. I will be talking to you throughout the week, letting you know when I'm going to try and schedule some Google Meets. It'll probably be Friday, just to touch base with you. So, yeah, feel free to give me any emails, comments on Classroom. But until then, I will see you later.